Hey there! Welcome to Keys Precalculus. I'm going to be going over section 1.6 inverse functions today. We did go over this in class, but I'm making this for anyone who wants a review or for anyone that was not able to be in class. What is an inverse? Well, an inverse mathematically is just an opposite. Okay, so for example, if I take the number 5, our numbers that we deal with have inverses, but they have more than one kind. The number 5 has an opposite number, an additive inverse. That would be the number -5. So the additive inverse of 5 would be its opposite, or the opposite on the number line, which would be -5. The number 5 also has a multiplicative inverse. It would be its reciprocal. So 5 is the same thing as 5 over 1, and if I take its reciprocal, I can write it as 1/5. Keeping that in mind, understand that numbers are not the only things with inverses or opposites. Functions can also have inverses as well. Take, for example, these two functions that I've written up here. I've got f of x equals x plus 4, and then I wrote its inverse, f to the -1 of x. That's how you represent an inverse, equals x minus 4. Let's show how they are inverses. If I do an XY chart, I can plug in numbers, any real values into x. That's my domain, and then I'm going to get out numbers into my range. So when I plug in 1 for x, or I evaluate f of x at 1, then I'm going to get the number 5 out. And if I evaluate it at 2, 2 plus 4 is 6. 3 plus 4 is 7, and 4 plus 4 is 8. So my ordered pair for this particular set includes 1, 5, or my set of ordered pairs is 1, 5, 2, 6, 3, 7, and 4, 8. This is not, this is obviously not the entire domain and range of this function, but this is the set that I'm working with right now, just to keep things simple. Now, let's look at the inverse function of x plus 4. It's x minus 4. If I were to plug in 5, or evaluate my inverse function at 5, 5 minus 4 is 1. At 6, 6 minus 4 is 2. At 7, 7 minus 4 is 3. And at 8, 8 minus 4 is 4. So the set of ordered pairs that I'm representing right now for this function is 5, 1, 6, 2, 7, 3, and 8, 4. Now, I want you to look at these two sets of ordered pairs. And what do you notice about them? Do you notice that each set of ordered pairs is reversed? The x in the green one is equivalent to the y in the purple one for each set. That means the domain of my function is the range of my inverse function, and the range of my function is the domain of the inverse function. My x's for my function are equivalent to the y's in the inverse, and the y's are equivalent to the x's in the inverse. If this is true for every x in the domain and every y in the range, that means that these two functions are inverses of each other. They're opposites. So I wonder what their graphs are going to look like. How are they going to compare? Well, let's go over to Desmos and see. Before I graph them, I wanted to show you the line, this red line, this graph of the line y equals x. That's my first red line that I put on here. This is called the identity function. That means for every x, there's going to be exactly the same y in the entire function. So if I plugged in a 1 for x, y would be 1. If I plugged in a 2 for x, y would be 2. It's going to be a straight diagonal line with a slope of 1 that rises to infinity. Its y-intercept is 0. This line represents the identity function. Now, if I were to graph the first one, x plus 4, my green one, that's a line that has the y-intercept at 4 and a slope of 1. Its identity function, or excuse me, its inverse function is going to be reflected across the identity function for it, because remember, for every xy in one function, its inverse is going to be the same. Its inverse will have a yx. So it would be reflected, its graph would be reflected across this red line, or this inverse function. So for every xy on my green one, it would be a yx on my red one, on my purple one. In other words, the 0.15 on my green one will be the same thing as the 0.51 on the purple one. They are reflected as if this red thing were a mirror across this graph of the identity function. They are reflected across the line that's represented by y equals x. That's because the domain of my function is equivalent to the range of its inverse. And the range of my function is equivalent to the domain of its inverse. For every xy in my function, I'm going to have the opposite xy. It's like a yx in my inverse function. So how do you tell if functions are inverses? If I give you two functions and say, are they inverses of each other, how would you tell? Take, for example, these two functions. F of x equals 2x to the third minus 1, and g of x equals the cubed root of x plus 1 all over 2. If I told you they were inverses and asked you to prove it, or if I asked you, are they inverses, what would you do? How would you figure it out? Well, one way is to do what we did earlier. You could create XY tables, find sets of ordered pairs, and see if those ordered pairs have opposite values. For every XY in the green, do you have a YX in the purple? But how many points would you not plot, but how many points would you figure out? Where do you stop? How do you know where the end is? Well, instead of finding the end, you could graph them, couldn't you? Because when we graph them, we see that every point is connected, and we can tell if it's reflected across this identity function, or the y equals x function. Let's go ahead and do that for those two problems. I'm going to erase the first two, and I'm going to put on the next two, the other set that I gave you. So we'll put the 2x to the third minus 1 up first, and we see that green function right there. We see that that's a cubic function, and it rises to infinity. There's a little bit of it looks like it's a little constant here in the middle. But let's see if this other one is reflected across the y equals x line, or the identity function. Let's see if it's reflected across that, and if it is, then we can say that these two functions are inverses of each other. Oh, yep, there it is. For every xy on the green, you can see that there is a yx, or the opposite xy, on the purple. And it's true for every point. You can see that very easily with graphing. But what if you don't have your graphing calculator or Desmos, or you don't want to graph it by hand? How can you figure this out algebraically? How can I figure out algebraically whether or not these two functions are inverses of each other? Well, before I do that, I want to go back to the number 5 we were talking about. Remember at the beginning of the video when we talked about the inverses of, for example, the number 5. So the additive inverse of 5 is negative 5. And when I take these two inverses and I add them together, I get the number 0. That number 0 is the additive identity for all numbers. What this means is I can take 0 and add it to any other number and get the identical number I started with. So 0 is the additive identity. So when I take a number, 5, and I add its inverse, I get the additive identity. The same thing is true when I take the number and I multiply it by its multiplicative inverse. Remember, the multiplicative inverse of a number is its reciprocal. And if I take 5, or thinking of this 5 over 1, and I multiply it by 1/5, I get 1. And 1 is the multiplicative identity. In other words, any number I multiply by 1, I'm going to get the identical thing I started with. So a number times its inverse gives me the multiplicative identity. So this same idea is going to work for functions. If I take two functions and I take the composition of each one, if I take f of g of x and if I take g of f of x, and they both reduce to the identity function, if they both reduce to y equals x or just the number x, or the letter, the variable x, which is the identity function, then they are going to be inverses of each other. Just like when you add two inverses, you get the additive identity. You multiply two inverses, you get the multiplicative identity. If you compose two inverse functions, you're going to get the identity function. So how do we do this? So I set it up here to take f of g of x. So that means I took my f of x here, and in place of the x, I put g of x. And then my g of f of x, so I wrote my g of x function, but in place of where the x would be, I put what f of x is. And now I'm going to reduce both of these and see if I get this identity function. So to start with, by order of operations, which we do follow, but we follow it a little differently when we're solving for x, I'm going to have to get rid of this parentheses first. So I'm going to take this cubed root of this thing, and I'm going to raise it to the third power. Well, this is the same thing as saying 1/3 times 3. So this becomes 2 times 1/3 times 3, or when I take the power is 1/3 and I raise it to 3. Then I'm going to be left with just x plus 1 over 2 on the inside minus 1. And then if I distribute my 2 or multiply it by that number, those cancel each other out. And I get x plus 1 minus 1, and I'm left with just x. Now if I come over here and I do the same thing with this function, I'm going to have to simplify this first. So 2x to the third minus 1 plus 1. This green parentheses is not really necessary here. It doesn't do anything because I'm not multiplying or distributing. So I'm going to rewrite my function here as just 2x to the third minus 1 plus 1 over 2. Now these two cancel each other out, right? When you add them, they cancel each other out. So I'm left with just the cubed root of 2x to the third over 2. And these two numbers also cancel each other out because they are inverses of each other. So I've got the cubed root of x to the third, and the cubed root of x to the third is just x. So you can see that both of these compositions of functions reduce down to the identity function. They both reduce down to x. Therefore, I can say that f of x is the inverse of g of x, or g of x is the inverse of f of x. And don't forget that it's represented, inverse functions are represented by this notation. If you've got f of x, its inverse is represented by f to the negative 1 of x. So g of x is the inverse, and I can re-represent it as f to the negative 1 of x. And what I just did was showing you how to verify or identify if two functions are inverses of each other. But now I'm going to show you how to find the inverse function of, or like if I give you a function and I say find its inverse if it has one, I'm going to show you how to do that. So if I say f of x is x minus 1 over 4, find its inverse, find the f negative 1 of x. The way you're going to do that is you're going to switch the x's and y's, because remember, for every x in my one function, I'm going to have the same y in my inverse function. And for every y in my first function, I'm going to have an inverse. The inverse function is going to have that x value. So I'm going to switch my x and y's. But before I do that, I need to write it with a y instead of an f of x. So I'm going to rewrite my function as y equals x minus 1 over 4. Now I'm going to actually write its inverse as x equals y minus 1 over 4. You see, all I've done is switched out my x's and y's. Now I'm going to solve for y. Just do simple algebra. To get rid of this 4 off the denominator, I multiply both sides by 4. So I get 4x equals y minus 1. Now I like my y on the left side, so I'm going to switch them around. I'm going to need reflexive property to do that. So anyway, so I've got my y minus 1 equals 4x, but I want y by itself. So I'm going to add 1 to both sides, and I'm going to get y equals 4x plus 1. Now, do you see that I've inverted everything? I've instead of subtracting 1, I'm adding 1, and instead of dividing by 4, I'm multiplying by 4. And this should be equal to f negative 1 of x. Now I could verify that by taking f of f negative 1 of x, and then also taking f negative 1 of f of x to see if I end up with just x for both of those. So my first one, f of the inverse of f of x, will be whatever I'm going to have to place in x minus 1 over 4. And what goes in this circle? F negative 1 of x, which is 4x plus 1. And when I simplify it down, 4x plus 1 minus 1 is 4x plus 0 over 4, and when we divide by 4, I get x. Then I'm going to do the same thing over here. I'm going to say 4 times, not x, but whatever the inverse of x is, which we say is x minus 1 over 4 plus 1. So if I distribute this, these can cancel, and I'm left with x minus 1 plus 1, which equals x. And yes, they both reduce to the identity function, therefore they are inverses, and I've done it correctly. Now let's talk a little bit about domain and range. What is the domain of my first function, f of x? We can see there's nothing restricting it because there's no variable on the denominator and there's nothing under a even radical. Therefore, there's no limit. So my domain is all real numbers. So then what is my range? Well, if I can put anything in for x, I'm going to be able to get anything out for y. It's going to be anything. So it's also all real numbers. Now let's look at my second function, the inverse function. Is there anything limiting this domain? No, there's not. And because there's nothing in this limited in the first range, in the function's range, my domain can be all real numbers. And my range, because there's nothing limited in my original function's domain to limit the range of the other one, my range is also all real numbers. And it would be that way anyway, because if you look at this function, there's 4x plus 1, there is nothing that you can't plug into x. There's no numbers there's no restriction of numbers that you can plug into 4x plus 1. So you can see that the domain of the original is the range of the inverse, and the range of the original is the domain of the inverse. Try another one. I'm going to give you f of x equals the square root of 2x minus 3, and I'm going to ask you to find its inverse function. But before we do that, let's talk about what its domain and range is. The domain of f of x can be anything that does not make what's under this radical negative. In other words, everything under the radical has to be a positive number. So what I have to do is I have to come over here and figure out, I say 2x minus 3 has got to be greater than or equal to 0 in order for this function to work. So I add 3 to both sides and I get 2x is greater than or equal to positive 3. If I add to both sides, I don't have to do anything, and I'm dividing by a positive number. So I don't have to turn the sign around, sorry. So x is greater than or equal to 3 halves. So the domain is x is greater than or equal to 3 halves. What's my range in this function? Well, the range is going to be, it's not going to come out as any negative numbers. If I make it 3 halves, I'm going to end up getting 0. And if I make it bigger than 3 halves, I'm going to get numbers that are bigger than 0. So my range is y is greater than or equal to 0. So my domain and range of this problem are different than the domain and range of the problem that we did previously. So that is going to affect my answer. It's going to affect my inverse function. Okay, so find the inverse function of f of x equals the square root of 2x minus 3. What do you say? The first thing we have to do is rewrite it with a y. Square root of y equals the square root of 2x minus 3. I switch out my x and y's to write its inverse. So I have x equals the square root of 2y minus 3, and now I need to solve for y. Well, I've got to get rid of this radical. So what undoes radicals? Squaring it. So if I square this side, I have to square this side. Remember, I'm squaring the entire thing. So I get x squared equals 2y minus 3. I'm going to switch the sides here. 2y, I'm going to actually just switch the 2y over. No, I'll switch the whole thing. Equals x squared. All right, I'm going to add 3 to both sides, so I get 2y equals x squared plus 3. And then if I divide both sides by 2, I get y equals x squared plus 3 over 2. So my inverse function is f inverse of x is x squared plus 3 over 2. But it looks like the domain of this would be all real numbers and so would the range, but it can't be. My domain of this inverse function is limited by the range of the other function. So I have to define it. I have to say it's x squared plus 3 over 2 when x is greater than or equal to 0. I have to do that because my range is not all real numbers. I have to limit my domain. So let's figure out what our domain and range is. When we look at this, if I'm limited to x is greater than or equal to 0, then that's my domain. It's limited to x is greater than or equal to 0. And so 0 is the smallest number I can put in here, so I'm going to put a 0 in just in my head. 0 squared is 0 plus 3 over 2 gives me 3/2. So what is my range? What is my range? My range will start at the number 3/2 and it'll just get bigger and bigger and bigger. Therefore, my range is y is greater than or equal to 3/2. Do you see how my domain and range of each of the function and its inverse have inverted or been switched? The last thing I want to talk about is one-to-one functions. Let's look at this function f of x. f of x equals x squared. If I plug in a -2, -1, 0, 1, and 2 for x values, I'm going to get a 4, 1, 0, 1, and 4 out for my y values. Is g of x an inverse function of this? Well, to take g of x, and I'm letting g of x be the positive and negative square roots of x. It appears that it would be an inverse function, but this is not a function because for every x I have, I get both a negative, like for example this 4, I get a -2. I also get a +2. For 1, I get a -1 and a +1. 0, I just get 0. Therefore, I can say that this f of x equals x squared does not have an inverse function because its inverse is not a function, because there's more than one y value for every x value I have. If a function is going to have an inverse function, it must be one-to-one, which means that there are no two elements in the domain of x that correspond to the same element of f. In other words, if a function f is one-to-one, then for every a and b in that function, the function of a is equal to the function of b. If that's true, that implies that a is b, because f of a can't equal f of b. You cannot have, well, just like in every function you said every x value has to be unique, well, in a one-to-one function, every y value also has to be unique. And so in order for a function to have its inverse, it has to be one-to-one. Look at what one-to-one means graphically. Let's look at this function x plus 4, which we found its inverse function, which was x minus 4. We can see that this is a function because it passes the vertical line test on the graph, right? That means that every vertical line I draw will only pass through the function one time. If it has an inverse function, if it's one-to-one, that means it will also pass what's called the horizontal line test. That means because of every xy, there's a yx, I can draw horizontal lines, and if it only crosses the function one time, that means that this function is one-to-one because there are unique y's for every x, and it has an inverse. And we knew that because, like I said, we had x plus 4. We found its inverse to be x minus 4 earlier. We can do the same thing for the next one. We had 2x to the third minus 1. Let's see. It's a function because it passes the vertical line test. Is it one-to-one? If I were to draw horizontal lines, yes, it would only pass through this green function one time. with the horizontal. This is not constant right here. Even though I said earlier, if you zoom in, it is not constant. And so it's just, you can't see the slope at this zoom. But if I were to draw horizontal lines, it's only going to pass through this one time. Therefore, 2x to the third minus 2x to the third minus 1 is a one-to-one function, and it has its inverse. It has an inverse, and we did find it earlier. Or rather, we looked at it earlier, and it's the cubed root of x plus 1 over 2. Now, I'm going to delete these and put up a quadratic function right here. Here's our quadratic. We know that this is a function because it passes the vertical line test. But does it pass a horizontal line test? No. If I were to draw horizontal lines, it would cross the graph twice. Therefore, its inverse is not a function. Therefore, x squared is not a one-to-one function, and it does not have an inverse function. Because for every xy on this yellow graph, there is not a unique yx. And we saw that earlier when we looked at the problem. I'll go back to it in a second. We saw that earlier when we looked at f of x equals x squared and g of x equals a positive and negative square root of x. They are not, g of x is not a function. Therefore, they can't be inverse functions of each other. X squared is not one-to-one. All right, I hope this helps. Y'all have a great evening, and I will see you in class.